So the next type of reaction we're going to look at are oxidation reduction reactions. So whereas acid-base reactions are about transfer of protons, oxidation reduction reactions are about electron transfer. So let me write that down while we're here. Oops, wrong one. So acid-base, that's the transfer of proton from acid to base. And in oxidation reduction, now we're looking at electron transfer instead. So an oxidation reaction is when an atom or ion loses electrons, and a reduction reaction is when an atom or ion gains electrons. So we're basically observing electrons produced in the oxidation reaction getting transferred to be consumed in the reduction reaction. And with that idea in mind, that's why we say one cannot occur without the other, because oxidation is producing the electrons and reduction is consuming the electrons. And that's what that little schematic is showing, is the transfer of electrons from one species to another. So the terminology for oxidation reduction sometimes gets confusing when you actually look at an example of a reaction. So I think it's a good chance to look at what we really mean when we're talking about how these reactions look. So kind of the classical mnemonic for oxidation and reduction is oil rig. Oxidation is loss, reduction is gain. So if we're losing electrons, that means it becomes more positive. And that's what we always expect to see in an oxidation. The loss of electrons makes it more positive. So in this case, you see iron turning into iron 3 plus cation, but in order to become plus 3, it had to release those 3 electrons. If I flip this reaction around, now iron 3 receives 3 electrons to become iron. So now it's becoming, now it becomes less positive. Right, we are losing electrons to go from plus 3 to neutral. So oil rig, oxidation is loss, reduction is gain. That tells us how the electrons are involved. Another one that I like to think about is just reduction reactant as a way to remember this. And what I mean by that is in a reduction reaction, the electrons are on the reactant side. So I think that more specifically helps you think about what we're looking for in the actual reaction, but this oil rig is kind of the classic one that we typically use. So in order for us to kind of determine what's going on during the course of a reaction in terms of whether it's an oxidation or a reduction, what we need to do is assign oxidation numbers to the species involved. A lot of oxidation number assignment you've kind of already done when you've been figuring out the charges of our ions. There are a couple more rules to add to that, but primarily we're already familiar with how to assign oxidation numbers for the most part. So when we think about what an oxidation number really is, it's basically as if we treat every molecule as an ionic compound. And we can say that by saying, imagine that electrons are completely transferred. So every atom in my molecule is going to have an explicit charge associated with it, and that's going to let us understand what the oxidation numbers are. And then if we observe that substance in a reaction, we'll be able to see how the oxidation numbers are changing. So again, like I said, you've kind of already done this to some extent. So first rule, just free elements by themselves, so just the plain old metals or the homonuclear diatomics like H2 and O2, or more unusual ones like P4 or S8. If it's just all the same substance, then we assign an oxidation number of 0. Mostly we're going to see that just for the plain old metals, but that's the way we would follow it. If we have some sort of ion, whatever it may be, this is also pretty straightforward. The oxidation number is just whatever the charge on the ion is. Now we get to rules where there may be some exceptions to it, but for the most part we can follow these. Anytime you encounter oxygen as part of our chemical formula, we're going to assume that the oxidation number is -2. The only time that's not true is with things like peroxides, which we won't really be looking at this point. Same thing for hydrogen. For our purposes, we're going to expect that the oxidation number is +1. There are unique circumstances where it can be -1, but not really anything we see in general chemistry. Rule 5 really goes back to everything we were thinking about with our single atom ionic compounds. So alkali metals being +1, alkaline earth metals being +2. Fluorine is always -1. That's never going to change. But the other halogens like chlorine, bromine, iodine, that's not set in stone. So they're frequently -1, but not always -1. And then the last rule is pretty important here. The sum of the oxidation numbers of all of the atoms in a molecule or ion equals the charge on the molecule or ion. So if it's a neutral molecule overall, then if we add together the oxidation numbers, we should expect to get 0. If it's a charged molecule, a polyatomic ion overall, then the oxidation numbers should add up to whatever the charge is. So let's look at this example down here. I know it's already worked out in the lower right corner. We're looking at the hydrogen carbonate ion. So what we want to say here is that the charge on hydrogen plus the charge on carbon plus 3 times the charge on oxygen, I'm going to put a little x there just so it doesn't look like 30, equals the overall charge on my polyatomic ion, -1. So the charge on hydrogen plus the charge on carbon plus 3 times the charge on oxygen equals -1. From our rules, we know what charge to assign to hydrogen and oxygen. We don't know what charge to assign to carbon. And that's generally how this is going to work, is that using those 6 rules above, we'll be able to assign oxidation numbers to all but one component of our, all but one species in our molecule, and then we'll just solve for the missing one. So that's what we did here by assigning -2 and +1 to oxygen and hydrogen respectively, 1 plus carbon plus 3 times -2 equals -1. So that becomes carbon minus 5 equals -1, which becomes carbon equals +4. So that's the way that we'll go about doing these, where we know what it's going to add up to. We assign the ones we can know from the rules above, and then figure it out from there. So the halogens is probably the tricky part in this. If we have a formula that already contains oxygen or already contains fluorine, then we don't know the oxidation number for the halogens. But if the halogen is just paired with a metal or with hydrogen, then we can assume that we know what its what its oxidation number is. So I guess let's just write unless paired with O or F. Okay, on this next slide we have oxidation numbers worked out for 3 different compounds. We'll just kind of walk through the work that I already did here. So we'll start with NaIO3, sodium iodate. So our approach here will be, we don't know what the iodine is, right? We know sodium because it's an alkali metal. We know oxygen because it's going to be -2 for our purposes. That's the information that we have here. So then in this case, we'd say the charge on sodium plus the charge on iodine plus 3 times the charge on oxygen. It's a neutral molecule, so we set it equal to 0. So here's our setup down here, right? 3 times -2, that's our oxygen, plus 1 for our sodium, plus the iodine that we don't know, and that all equals 0. So that makes iodine minus 5 equals 0, which becomes iodine equals plus 5. Okay, next one, I guess IF7. So here's another case where we've got our non-fluorine halogen paired with either fluorine or oxygen. So this one's pretty straightforward. We're basically going to say, since we know fluorine must be -1, if it's IF7, then iodine has to be +7. Okay, this last example actually looks like the one I have worked out on or I have for us to work out on the next slide, but I guess that's okay. K2Cr2O7, potassium dichromate. So in this case, we know potassium because it's an alkali metal. We know oxygen because it's going to be -2. So there are those values here. So 7 oxygens at -2 each, 2 potassiums at +1 each, and then 2 chromiums at we don't know yet. So what do we end up with after this step? When we clean that up, we get 2 chromium minus 12 equals 0, which becomes 2 chromium equals 12, which when we solve for it becomes chromium equals +6. Okay, so hopefully you're seeing the pattern here, right? For the most part, I'm basically just looking and saying, which ones do I know, which one do I not know, and then solve for the one that I don't know. Okay, last slide for this very short video. We already did this one, right? I need to change that to something new. I guess I didn't notice that when I made the problem. But here are some where we want to assign the oxidation numbers. So if we look at the first one, fluorine we know, manganese we don't know. And these are all neutral molecules. We'd say manganese plus 2 times the charge on fluorine, the oxidation number, equals 0. So that becomes manganese plus 2 times -1 equals 0. So that means manganese equals +2. For these simple ones, it kind of goes back to ionic compound naming, right? I should be able to look at MnF2 and say, fluorine makes -1 fluoride. There's 2 of them to make -2, so the manganese must be +2. That'll more or less apply on the next one as well. We know chlorine, we don't know titanium. So in this case, I can say I do know chlorine is -1 because it's not paired with oxygen or fluorine, so we need to assume it's going to be -1 in those conditions. So that's the way we want to think about it for chlorine, bromine, and iodine. We expect it to be -1 unless it's paired with oxygen or fluorine. So here we just say titanium plus 4 times the oxidation number of chlorine equals 0. That becomes titanium plus 4 times -1 equals 0. And then that just becomes titanium equals +4. Same thing, I should be able to look at TiCl4 and immediately name it titanium 4 chloride, but this is the way that we would work it out. Okay, 2 more of these. So KMNO4 and H2CrO4. So KMnO4, we know potassium as an alkali metal and oxygen to be -2. So in this case, it's manganese that is our question mark. So it'll be potassium plus manganese plus 4 times the oxidation number of oxygen equals 0 again, since it's negative or neutral overall. So 1 plus manganese plus 4 times -2 equals 0. That becomes manganese minus 7 equals 0. So manganese equals plus 7. So this one's a little trickier, right? We kind of have to solve it like the ones on the previous page, but in the first two, I just wanted to show you there are cases where in theory you kind of already know the oxidation number. Okay, one more of these, H2CrO4. So it'll be chromium, our transition metal that we don't know, hydrogen and oxygen that we do know. So now this would be 2 times hydrogen plus chromium plus 4 times oxygen equals 0. That will become 2 times 1 plus chromium plus 4 times -2 equals 0. And this would turn into chromium minus 6 equals 0. So chromium equals 6 plus 6. Okay, we already did K2Cr2O7. I guess I just copied it over and didn't notice. So that's a good start with oxidation reduction stuff. So if I gave you an isolated half reaction, you should be able to tell me whether it's an oxidation or a reduction. If I give you a chemical formula and ask you to tell me the oxidation numbers for all the components, then you should be able to do that as well. So just kind of a brief introduction into this topic in this chapter. If you learned how to balance oxidation, reduction, full reactions in a previous class, that's great, but again, that's something that ends up getting covered in the second semester class instead of right now. So yeah, I guess let me go ahead and stop here. I think we'll need 1 or 2 more videos to wrap up the last bits of material in this chapter.